Good afternoon again. As I said, this is the second video of today, and it is a very long video, so it covers the rest of today, next week, and probably part of week 7. I already mentioned it before. This is a completely different way to go to achieve the same result that we have achieved in the last few weeks. It's a way that is potentially extremely promising in the sense that it seems to be actually a natural way. We have evoked this kind of thinking a few weeks ago. But we'll see is also a very hard problem. So we will first look at the kind of architectures that we want to do in hardware, and then we'll look into how to generate programs for these architectures, since they are not compatible immediately with the architectures that we have seen so far. So we will need to build a special compiler for them. Enjoy this. I think is an interesting trip in a completely different type of architectures, and there is something very, I think, appealing intellectually to these kind of architectures.
What we have done so far is one way of building a processor that exploits ILP, instruction level parallelism, that tries to go faster by not executing one instruction after the other, but potentially trying to start several instructions at the same time in the same cycle. What we're going to do now is try to do it in a completely different way, right? We throw away everything that we have done and we try to achieve the same goal in a different way. It's a class of processors that are called most commonly as VLIW, very long instruction word, and if you have never heard of this, you'll see very soon why, or sometimes called EPIC. You probably heard me saying that Intel never uses the same name that everybody else has used for something. They always have to do a trademark and a new name. And in this case, they called it EPIC. And it's actually a good name for once, because while a very long instruction word is not very descriptive of what is the characteristic of these machines, EPIC is. It says, it means explicit parallel instruction set computer. So it's a computer where the parallelism is explicitly written by the programmer. And again, you'll see in a minute what that means. So again, we've done a path, right? We've gone from this standard processor of the 70s, late 70s, into a machine essentially like the one that you have in your laptop and that is probably populating most of the data centers and so on. And we want to go back up to one step, the step when we did pipelining. We'll keep at least partially the idea of pipelining. We'll definitely keep the idea of pipelining, but partially the way we implemented pipelining. And from there, we'll go somewhere else. So we started from this machine that is completely sequential, the instruction. So we had pipelining to achieve ideally a CPI, a number of clock cycles per instruction equal to one instruction produced per cycle, which of course never really happens, but is the ultimate hope that we have with pipelining. And again, we don't throw this away. We try to have multiple pipelines running at the same time. This is what we have done before. This is still what we are trying to achieve. Again, the pipelines will never be completely full all the times because of all the problems that we know, but we are trying to do it again. The point is that we are going to do it in a different way. And so what is different? What are we going to change? For this, let's go back to our dynamically scheduled superscalar processor, so the processor that we have done, that we have studied, and let's try to have a 10,000 meter view of it, right? From very far away, what it looks like is register file, branch of units, on one side, this is the processor. On the other side, there is a program that is a sequential program, right? That there is a sequence of instruction. We may disobey the sequence, but it still counts as a sequence. And what we do in between is a lot of stuff, what we have studied in these weeks, a lot of hardware, very critical hardware, that has no other real benefit or purpose than to read these instructions from the sequential code, rearrange them however we see fit, and emit them and issue them to the functional unit for executing as quickly as possible the program. So this dynamic scheduler is essentially everything that we have done, right? Reservation station, scoreboards in some techniques, reorder buffer, all those things that we have put in our processor is in there, and is a big part of it. So what is this box dynamic scheduler? What does it do? The only thing that does, and maybe it's not only, but the thing that it does is to take one decision: when each instruction can be executed and where, on which unit. Now, let's go back to what we discussed a few weeks ago when we started looking at the pipelining and the problems that already came up at pipelining, at the time of simple pipelining. And what were these problems, right? These problems were essentially two. The fact that we have control dependencies and the fact that we have data dependencies. So let's think of data dependencies for a minute, right? Data dependencies means we have to figure out if between two instructions there is the same register that is used in the first one as a destination and in the second as a source. And this is the worst thing that can happen for our pipeline, because we cannot let the second instruction advance until the first one is completely executed. If you remember, we discussed at the time, we said, okay, so what can we do about this problem, right? And we went down one of the paths, which was to say, okay, so if I need to figure that out, and I need to stop the pipeline so that the second instruction doesn't execute, right? Then we try to complexify, in some sense, this idea by saying, okay, well, I stopped this one, let me see if I can do something else, right? I hope you remember and have very clear this idea. But at the time we said, maybe there is something else that I could do, which is change the code, right? And we went actually in two steps, but they are conceptually the same thing, which is to say, okay, we need to put space between these instructions so that the first one is executed. So why don't we put some NOP, NOPs in between, some instructions that do nothing in between, so that they are spaced enough. Essentially, this is what our stalling the pipeline does. So it's exactly the same thing, except that I look at it before and I put the NOPs. And once I put the NOPs, there is another thing that I could do, is to say, okay, but now that I put the NOPs and I have some spaces to do something, why don't I bring the information? And remember, the point is doing this at compile time, doing it as a programmer instead of doing it in the R. And this is exactly the idea that we are going to pursue here. The point is, why are we putting in all this very complicated hardware to detect dependencies and to handle properly dependencies? Think of what you see, for instance, in the homework about the R10000s, all these tables to do the renaming, all these queues and so on. And think, this is, to a large extent, and of course I'm exaggerating, but let's say only to discover that one instruction is producing a value and the next instruction needs that value, and so we need to do something about that. So why? Why wait fraction of nanoseconds before the instruction is executed, or just after I fetch the instruction, to figure out that thing which is clearly written in the program, right? And I could detect before. And we said, and we'll come back today to that point, one of the reasons is that this exposes some parts of the microarchitecture and makes the code incompatible. But if we leave this aside for a moment, and we'll again come back to this, why all this complexity? What justifies doing all this complexity? And this is exactly the idea that we are going to try to pursue. Why don't we do the scheduling completely at compile time? There are many reasons for that, right? One of the reasons is not only in terms of timing, right? That the critical path these days is no longer, I may have mentioned this already once in some context. The critical path used to be in, I don't know, my multiplier, my floating point unit, right? And people were looking at arithmetic, computer arithmetic, as one of the key problems to solve for making processors faster, right? Can I do the multiplication in a different way, in a more efficient way, in a faster way? Now this is gone, long gone. The critical path of processors is most definitely in all these resources, in these resources that are here in the dynamic scheduler, in all our associative searches that we have been trying to avoid as much as possible, in all these queues and so on, there is the critical path. I always tell a story, I think it was the Pentium 4, I'm not sure exactly, but one of the early, relatively early Pentiums. And they moved from one technology to the other and from one generation of the Pentium to the next. And as always in industry, you don't restart developing a processor completely from scratch, right? You have done a lot of things that worked super well in the previous one, and you want to keep them going, right? You sort of, you just bring them in the new technology, and maybe you use them in a slightly different context, but it's exactly what you had before. So there are also considerations like risk, right? It worked, so you cannot make a mistake if you take the same. And in this spirit, they ported, for instance, the adder, right? The maybe at the time it was a 32-bit adder, I don't remember. Yeah, it was almost certainly a 32-bit adder. So they brought it to the new technology. And discovery is that the new technology being faster and so on and so forth, the addition, the ALU that needs to do the addition, if it needs to do an addition, it does it in less than half the cycle. So it's so fast that they decided to use the same adder on the two halves of the cycle, on the two edges, basically, of the clock, which is always a not very clean thing to do, but is also safe if you understand what you're doing. And so basically pretending that they had two ALUs in their superscalar processor, but actually there is only one ALU and is being used twice in the cycle in the two halves, right? And again, this tells you how arithmetic and data path has gone out of the critical path. The problems are somewhere else today. And so this is the part of the motivation of saying, why shall I put all my resources, all my transistors in this logic for sequencing, for scheduling, instead of reasoning better at the time I'm writing my code. There are other considerations that you can make and ask yourselves is about the testability, right? All these out-of-order machines become incredibly hard to test. And I think that outside of industry, we have very limited ideas about how they manage to do the testing of these machines. Imagine to do typically processors are functionally tested, right? I have a multiplier, let's write a program that does a lot of multiplications. Let's reason very well which operands to use so that we do a minimum number of multiplications, but we try to see that all the bits can change, all the calculation can be done, right? That is the type of normal way of doing tests of processors. Now imagine that you have one of the machines that we have been working on, and you say, I want to try to do every multiplication on every one of the 3 multipliers that I have in the architecture. But how do you create a sequence of instruction in such a way that you're sure that a specific multiplication will be executed into a specific multiplier? You may not know, right? Typically, you don't know which multiplier has been used. But if you need to test, you need to know where it goes. And this may depend on a number of things that you don't control, like cache misses and so on in your program. So you need to also write your program to have the cache misses that you need, or vice versa, the program done appropriately given the cache misses. So it's incredibly difficult, right? And maybe other techniques are also used, but you see how much complexity comes from this. So it seems a great idea to try to get rid of it. And one part also of the story that is probably losing a bit importance these days, because we know that there are other limits, and we have even alluded to in the last couple of lectures. There are other limits to the exploitation of the parallelism at the instruction level, like branch predictions, the fact that you don't know what is the code to be executed if you search too far away for new instructions. But you do understand that there is this intrinsic sort of dependency from the square of the issue rate, right? You tend to, the more instruction you have that you want to issue at each cycle, the more you'll have in the pipeline growing more or less linearly with that. And you need to check dependencies with all of these, which is a number of checks that is of the order of the square of the issue rate, right? So this is not really sustainable if you want to go further. And again, maybe you don't want to go too much further in this direction because of other problems, but if you wanted, and if in some context it would make sense to do it, this would be a problem. So what is the idea, right? Again, let's go back for a second to this. I have this logic here that does nothing else. Again, it may not be so trivial, but it's nothing else than deciding what at every cycle each of these guys should be given an order to perform, right? Sort of what is the package of job that they, or task that they should take every cycle. And so what is the idea? The idea is a bit like imagining that you go there and you take a picture of what has been rescheduled after understanding what can be scheduled, and somehow using this directly as the program, right? Or in other ways, and more reasonably maybe to describe it, is compute this transformation from a sequential non-parallel code into an explicitly parallel code. Again, see the name that we have discussed before, right? By Intel, is explicitly given. I have here an instruction, and this instruction, very long because it contains many sub-instructions or several operations. These instructions tells exactly what should be done by ALU1, ALU2, the floating point units, and so on and so forth, without anybody between me and the units that decides whether we should block, wait, not wait, reorder, and so on. It's just, that is what should be done, and I compute it at compile time. So the hope is that I'm putting the resources where it needs, right? And whereas in a superscalar processor, the compiler scheduling is very limited. GCC certainly has an instruction scheduler. There are instruction schedulers in typical compilers to try to order, let's say at best, the instructions. It doesn't quite matter, or it matters only to an extent, because afterwards everything is done at runtime and every reordering is done at runtime. So in some sense, you want to help the machinery that does the reordering to see the right instructions as early as possible. It was not like this before having dynamic scheduling, the first super scalars. You would have to do a very careful scheduling in the compiler to manage to exploit the super scalarity. Now that you have out of order execution, essentially you don't care. And now we want to do it completely at compile time. So let's look at it. The code changes dramatically and is more dramatic than just the superficial view that you can have in this picture, right? Here we have the traditional code, and the traditional code says do op 1, when you're done, do op 2, when you're done, do op 3, and so on and so forth, right? You may not be doing that. We have started doing something else, but that's what the code says. That is the semantic of the code. What this code says is something very different. It says, on the first cycle, do op 1, 6, 7, and that's it. In the first functional unit, in the second functional unit, do this, and in the third functional unit, respectively. So this column corresponds to functional unit, but more importantly, this set of operations are meant to cycle 0 or cycle 1, whatever. And these instructions are meant not to be done later at some time, but the next cycle, and then the next cycle, and so on and so forth. So the difference, the very fundamental conceptual difference, is that here instructions and cycles have nothing to do. There are instructions, and there is only a notion of sequentiality between the instructions. People call it also latency independent semantics, in the sense that I have no idea how many cycles operation 1 will take, or people call it unit assumed latency, in the sense that in my head I say, okay, do operation 1, it takes 1 cycle, then operation 2, it takes 1 cycle. I don't know, it's irrelevant, right? And so in my mind, I think it of 1 because it's simple for my brain, but it's irrelevant. And here, I cannot assume unit latency. There is a specific latency, and the semantic depends on this latency, right? For instance, here, when I see operation 2 here and not here, it's absolutely clear that operation 2 must be here because there is a dependency on instruction 1, right? If it is the second, can only be dependent on the first. And why is it scheduled here and not here? Because whatever operation 1 is, clearly it's in some sense visible in the code. It takes 2 cycles to perform the operation 1, and so operation 2 can only 2 cycles later consume the operand, this operand on which there is the dependence, right? So it's a completely new notion of how this is, and one of the is constructed, and one of the things that you notice is that there are knobs, right? This program has no knobs, right? Because, I mean, people use no ops for some reasons, but they are weird reasons somehow. They are not a real constituent of my code. Here, no ops or knobs are fundamental parts of the code, because since I have to say explicitly what this unit will do in every cycle, well, I know that very often I don't know what to do with that unit, and I should put a no op. Remember last week when we were discussing the simultaneous multi-threading, right? And I hope you remember my little drawings where we have all these issue slots that are used. and essentially these are issue slots, right? It's the code is written in terms of the issue slots. I put it in the program because I want to issue this instruction. There is nothing between, again, me the code and the functional units. And then you remember that there were a lot of these spaces that were yellow, that were empty, and we were trying to do something to fill them up with simultaneous multithreading. Well, everything that is yellow, now I have to put an instruction and I have to put a NOP because I couldn't find anything better. So again, once more, what do I expect from this? I expect to use better my transistors, not to put transistors in doing a job that I can comfortably do at home before in my compiler. And the second is to get a timing advantage, because that part of the processor is most likely my critical path, constitutes my critical path. So if I remove that logic and I keep the functional units, I sort of go back in a better place where I can go higher clock frequency or shorter latencies and so on and so forth. One way to, becomes a bit redundant, I guess you got the idea, right? One way of looking at it is that between a program and the execution, there are a number of things that need to be done, some optimizations that every compiler does, and then you start doing dependency analysis, you decide the resources that you use for this until you execute. And most of these things in this list are done in the superscalar in hardware. So I end up here and I emit the code a little lazily, and then this code will go through this during prime time. And now for a VLIW EPIC processor, all these things I need to do inside my compiler. So my compiler job is going to be more complicated, but if you think lightly to this, if you think longer, we'll see that things are more difficult. But if you think lightly, these are not very hard things to do, right? It's if it were that what you need to do there is only understand when there are dependencies and want to schedule it appropriately the operations, well, it's not a great job. That's exactly part of the motivation, is why are we waiting the last fraction of nanosecond, quarter of nanoseconds before deciding when to do things. Let's decide it before and comfortably. And the comfortably is one part that is important, right? Why there is a comfort in doing it in the compiler? Well, the comfort that you have in the compiler is that to take these decisions, you have a lot more information available, and as we just said, a lot more time available, right? So if you ask me some important questions about how the order should be done, what are the properties of the code, I see the complete code, right? I mean, I have a global view of the piece of code, whereas my instruction scheduling in hardware has an incredibly narrow view, right? It takes the next 4 instructions and compares with, in maybe trivialish way, with the last 20, 50, 100 instructions and takes a decision immediately, right? So the decision is very quickly taken, and the sense of context where this decision can be taken is extremely limited in hardware, whereas in software, I can do analysis. And I don't have 1/3 of a nanosecond to take a decision. I have maybe even seconds, right? Seconds are a lot of time, and the users are very unhappy, but milliseconds, microseconds to take decisions. So the analysis I can do here is way more strong, performant, and so on. The other part, and we'll see that this actually counts for quite a bit, is that we don't know the data we are operating on, the numbers that are in the registers, for instance, right? And we'll come back to that. This is a very severe limitation. At the same time, a priori, it's not clear that one doesn't compensate the other, right? We'll not have this because if I'm in the compiler, I don't know what is the value in a register at a given point in time, but I have time to think about maybe what are the properties of the values that can be in the register file. In some cases, I may know a lot because I have the program here that computes this value. So I don't know the value, but I know how it is computed. And from how it is computed, maybe I can know something. I can know that a value is always odd because of the way I compute it, right? And maybe this is useful. So we'll come back to this at a later time. So what are the challenges of going down this path? We'll see three of them. We'll start with the second and the third. The second, we already mentioned it, is the binary incompatibility. I think it's perhaps already clear, but we'll go a little bit deeper in a minute to understand to which extent this change of semantics precludes the any change in microarchitecture or virtually any change in microarchitecture. I can advance already from now that we don't have any real solution for this. We'll come back to this in, I think, 2 weeks when we will be discussing dynamic binary translation, which is maybe the only thing that we can do is a sort of a cheat to solve the binary incompatibility. We'll not have the binary ready until just before, right? Because the binary is intrinsically incompatible. So we'll not solve the second, but we'll try to understand it. We have this problem of the NOPs, the NOPs in the code, and this we need to do something because it has some damaging effects, but it's actually not, at least at first sight, at the first level of analysis, is really not a big problem to solve. And then we'll come later to the first problem here in this list, and we'll spend the rest of today and the week after to look at the compiler technology and how the scheduling can be done. So this is the problem that apparently is very easy because that's what we said until now, and actually we'll figure out that it's not easy at all, but we'll try to develop a number of techniques that can help us do it. Okay, so before closing this lecture, and then we move to a bigger lecture that is covers both this week and next week for the compiler technology, let's look at the second and the third problems that are more easily taken care of, in the sense that, as I said, one we don't solve, but the other we do. So the first is the code bloating problem. We have these NOPs, and are they a problem, right? This is my code. And now my code has a lot of NOPs, and these NOPs are nothing terrible a priori, right? It's just something that says, don't exist. So the question that I have for you, and this is my usual pose that we do these days, is this a problem? Shall we really bother for that? I mean, what's wrong? One of the first consideration that comes to my mind is, okay, my code is going to be, say, even 3-4 times bigger. But first of all, how much is my code when I put it in, well, on the disk, we don't even start talking, right? When it is in my DRAM, how big is the code that I put in the DRAM is probably a very small part. And it is my DRAM, I have 32 gig in this laptop. I really don't know why and what to do. Well, these days is to do videos and recode, but in general, it's really not used and not of particular use. So, and it's very cheap. So the question to you is there a problem in having so many knobs? So let's do a little pause. So why is it a problem to have the knobs? Again, when I ask it, is because there is going to be a problem. The problem is not so much when it is in DRAM, but if it is in DRAM, it will also come in my caches, right? And especially the first level cache in every processor is very limited by some strange considerations. We don't have time to go there. I will do it if we were maybe in presence, but everybody understands that the first level cache is very limited. Now I'm using maybe 3 times, 4 times more of my cache for putting the knobs, which means that I will have way less chances to find my, I don't know, inner loop or my code, relevant code in the cache. So it's not so much of not a problem because memory is cheap. Caches are a problem, right? So what can we do about this? So the first analysis, the first level of analysis is why there are knobs. There are knobs because of I don't know what to do. Again, what I said before, think of the last lecture on simultaneous multi-threading and these issue slots that I could not fill, the yellow one that I have. This is just an encoding problem, right? I have a few of these that are knobs. Instead of putting a, let's say, imagine that each of these instructions is a 32-bit. Instead of putting in each way of my VLIW 32-bit to say it's a knob, I can do some encoding that is less costly, right? You can see an example below. It's just an example, but it gives you a sense of the kind of things that one could do. It starts from here, right? And it says, well, what we have to do is to do an add one, the add one instruction in the lane B in the second column, in the second functional unit. And this is the last instruction for this cycle, right? So this is an encoding where I have taken the only information that I had here, which was missing information, which was I want this in the second lane, and look, these are knobs because there is nothing else. I have encoded in these few bits, right? This is, in this example, is probably 2 bits, and this is a single bit that says where things are. So there is this thing that is, some people call it the stop bit, the one that says we are done, and an explicit encoding of the destination functional unit, of the functional unit I'm encoding for. And you see here another example. If you go one cycle later, right, there is a load that I need to do on A, but there is something more. There is an add 2 that is to be done on the unit C, and there is some more. And there is a mul D that has to be done on the D, on the 4th column, and this is the last one, so we are done. So whatever I've not said, I said something for A, something for C, something for D, whatever I'm not said at this point becomes a knob. Now you can imagine that the logic for doing something like this is a bit maybe annoying because, okay, we are starting making compromises on the simplicity of our machine that was I fetch and I immediately throw the instruction directly to the functional units, and I do absolutely nothing. Okay, I start doing something, but it's not a terrible job to do, right? It's just a bit of steering. Well, steering is a bit costly because the crossbar is costly, especially if I don't have 4 units, but I have 16 units. It's going to be a bit rougher, but it's feasible, right? And so this is encoding, and in a sense, this is gone. We will see later that is not true. We have removed, ideally here, completely the code bloating, the growth in code due to this new paradigm. We have brought it back essentially to the same size as before, plus a few bits here that are almost irrelevant. But we'll see that there are other reasons why the code will grow again. And we'll come to that later even today. So the second problem that we want to look at it before we change gears and we go in the big problem, which is the compilers, is the binary compatibility. And we discussed this a little bit already, so let's not spend too much time, except to understanding that what we are doing exposes a number of things about my architecture. And I'm sorry, I said the wrong word, about my microarchitecture. So a few things that normally are microarchitectural knowledge, like the operation 1 executes in the first unit in 2 cycles, which is what is intrinsically written and necessary for a compiler to write this code, because I need to know that operation 2 is here because of the dependency. This information is typically an information that is microarchitectural in the sense that is not on the manual for the compiler, right? If I go and I look how long it takes to execute and add one specific instruction in an x86, at best, I have some indications from Intel. Maybe I get some information from some strange website that does this kind of analysis, and is certainly not a guarantee, nothing, right? And it's varies a lot depending on the type of processor I have from Intel, despite the fact that the code is the same. Here, this information has to be part of what I tell the compiler to write the code, to enable the compiler to write the code. I have other information. There is this information here. So I have 4 columns. Why do I have 4 columns? I have 4 columns because I have 4 functional units. Aha. So now if I have 5, my code is completely different. If I have 3, it's completely different. So people have been looking at this a lot to try to circumvent these problems, but these problems are not easily solved. There is no simple way to address this without going back to the dynamic scheduling idea. One of the things that are maybe worrying but not critical is that, for instance, if you do a new version of the processor, you would typically only add the new functional units, right? You have more transistors, more slow, and so you say, I had only 1 floating point unit, let me add a second one or something like this. So in this case, if the direction of evolution is only one, is sort of monotone, and you only add the things, it's okay, right? You could have some parameters, some information that tells your processor that you want to use only, in this example, the first 5 units here, and you have nothing specified in your code for the next 2, right? So this could be possible, but keep in mind, right, is a terribly bad idea, not critical, not impossible, but still a terribly bad idea, because I'm giving you the code for Photoshop for a 5 execution unit version of the processor, because that's what you have. You play around, you're doing things, and then you go out and you say, oh, no, I want to buy a new computer because I want to go faster, and my computer is becoming old, right? And unfortunately, we do this all the time, everybody, right? And you get your new beautiful processor that has 2 units more, but now your code, yes, it works, it's already something, but it doesn't exploit the novelty, right? The new one. And this is not something that users appreciate, right? Because if you change your computer, is to get faster. So then you need to have the binary incompatibility. You need to go and ask Adobe for a new version for you. So there are a few things that are interesting to pay a little bit of attention to. One is self-evident, right? The latency cannot increase, because if you increase the latency, well, of course, your dependency is not honored. I want to repeat this once more to make sure that everybody is in the same page. These processors, at least in the basic incarnation, in the basic formulation, have absolutely no stalling logic, right? It's part of the game, it's part of the advantage is that they are completely blind to dependencies, right? So if I don't do the perfect job, the correct job, they will just execute incorrectly. And so this is, I think, very easy to imagine in this case. If I go for higher latency, of course, the dependency is violated and nothing works, right? The problem is, do we ever increase latency, right? One could think, but look, how come that I increase my latency? Finally, my transistors are faster every generation. It may not be so true anymore, but still they will never become slower, right? And so is this really a problem? Could I guarantee that whatever I do in the next generation will not increase the latency? And that is not so easy, right? And you have an example here that is a bit caricatural, right? But suppose that you have a load and an add. They correspond to two very different uses of technology, because the load is a memory access and depends on how you use transistors to create memory. And memory, even a cache, right, is memory. It's not the DRAM, it's not a completely different technology, but uses transistors in a different way because it's done it's essentially an analog circuit. To be so fast as we need it, is essentially an analog circuit, very sophisticated. The add is actually done by gates, our normal logic circuit. And the way the progress of these two ways of using transistors do not match. As it has been said to you probably many times, the memories improve less well. And again, it's not typically what people tell you, because when you have the memory wall and so on, kind of buzzwords, what people are thinking are DRAM getting absolutely not improving as fast as logic gates. These load in cache, because if it is not in cache, well, that's a disaster. It will take 100 cycles. We're not even talking here. But if it is a cache and a cache hit, it's the same type of transistors at the add, right? But it's still a circuit that is done in a different way. And therefore, maybe the add in a new technology goes faster, but more faster than the load. And what is the situation is that maybe the add is what I use as a principle to define what is my cycle. And now the load that is a little longer doesn't fit anymore, and I prefer to put it onto cycle. Now you think, first of all, is that a problem? Yes, right? We have this situation where my latency of the load has increased in number of cycles, so it's a problem. Does it happen? Is it realistic to think that this may happen? Yes. If you look at it, if you go and try to find on Wikipedia some statistics about how long it takes a load, or what is the latency of the cache level 1 of modern processors, it's very often 1 or 2 cycles, and it maybe is not one every time, but can be 2 in some special situation, but it can be 2, whereas until fairly recently, it was self-evident that a level 1 cache will take not more than 1 cycle. So it's exactly this problem that has happened already. Okay, so this is half of it. And so the part that seems naturally to be bad is actually bad, and even if processors get always better. Maybe it's interesting to look at the opposite part, which is And what about if latency decreases? Because that might happen more, right? I have a new architecture to do a floating point unit. And of course, I want to use it, right? If I discover that I can do a logarithm in 3 cycles instead of 4. And that is also an interesting fact, because imagine the code on the left, right? And there is these dependencies are emphasized by these lines. So there is this A, that is this dependency, E and C. These are the 3 dependencies, and this is a reasonable scheduling, right? And for some, assume that the division, which is the first operation, takes longer than all the others that take 1 cycle, just for making the example, right, the numerical example, and this is the dependence, right? So this is 2 cycles later, everything else is done like this. Okay, so everything fine. Where is the problem? Well, these are variables, right? So we need to do register allocation. We need to think of which registers of my machine I'm using for these variables, right? A, B, C, D don't exist. They exist register 1, register 2, and so on. And so one of the things that I can do is to say, okay, look, my compiler has one fairly reasonable allocation that says this A, this register, will actually become used here, right? Because the write back of this instruction will take is 2 cycles later. So here I need to write into a register, and at the beginning of the next cycle, I'm going to read that register. Fine. Here I need a register where here I'm going to write in a register at the end of the cycle, and at the beginning of the next cycle, I'm going to read from this register. So the liveness of the register, the time these registers need to be alive, is for the one holding C is here, right? Is across these 2 cycles, and for the register holding A is across these 2 cycles. Now, I don't know how much you know of register allocation, but the intuitive idea is clear, right? If you have 2 registers, 2 values that need to be held in the registers at different times, here and here, you can use the same register, right? Recycle the same register for the 2 values, which is what a compiler could do here, right? Assign R1 for C, uses here, and assign R1 again here for this. But now we have a problem, right? Now is, if I have my result from the division that comes in 2 cycles because I improved my divider, I have a problem. I have a problem because now I want to write back in this end of cycle. It will stay in normal cases, in general, this is not a problem, right? It will stay in the register for 1 cycle and then it will be taken out. So why is that a problem? Well, it is a problem because I'm writing here in a register where I'm writing another result. And this result will be supposed to go out, but now there is my result too, so I don't know what will happen. There are some problems even in the hardware if I write in the same register, but that's not what concerns us. What concerns us is that certainly whatever the machine does is not going to do the right thing. Okay, so this is a little counterintuitive, but it tells you how many problems there are in binary incompatibility. You cannot change the number of units, you cannot change the latency up, you cannot change the latency down. Essentially, everything that you try to change is exposed to the programmer or to the compiler and is constraining. So, as I say, binary incompatibility, we give up, and we'll come back to this not next lecture, but 1 lecture later, to do some, in a sense, some cheating not to handle that problem, because we cannot handle, we don't know how to handle it. Code bloating, we think we have solved, but we'll come back to this by noticing that actually we solved only the most superficial part of it. And what we are going to do now is to look at the compiler technology and realize that is actually what seemed to be, oh, a trivial job, let's not wait the last minute to do it, let's do it before, actually done before, it's pretty tough job. We come now to the main problem that we are going to have, which is the compiler problem. We need the compiler to do the job for which we have removed all this hardware in the processor, and we want to understand how complex is this job. And the first thing to do maybe is to make a little example, take a little example and go through it together as if we were a compiler to see how difficult this job is. We'll discover that it's not terribly difficult, but we may be a bit disappointed with the result. So here is the example, is a pretty trivial program, right? It's what is reading from memory, adding something to whatever has been taken from memory, putting it back exactly where it came, and incrementing for some time. So what we are doing is essentially adding a constant to a vector, right? So it's a silly program, but it's not a completely unrealistic program. It has a bit of everything. And we want to execute this program written in MIPS or whatever is pseudo MIPS, this language. We want to schedule it, write it for a machine, a VLIW processor that has 3 slots, so 3 columns, one for the load store unit and for the branch unit, so it's a single column for both, one for the ALU and one for the floating point unit. Notice here that all these are floating point operations, whereas, of course, the operations on R1 are fixed point operations. And we have the other information. So this is already an information that, as we said before, is unusual or not known for a normal superscalar processor, but here the manufacturer tells us exactly what are the slots that we need to supply instruction for. And the other information that is microarchitectural information that suddenly has become architectural information, that is information that I need to compile, are the latest. So let's schedule this code. Let's do the work that we want our processor to do. Let's do it together.
So we have been told that the machine has 3 units. So preparing the code will be scheduling over the 3 units our instructions and at the right time. So the 3 units being the load store plus branch unit, the ALU, the floating point unit. So we start scheduling and we can apply whatever algorithm we see fit. Is a sort of trying to schedule things as early as possible seems the most reasonable thing to do, right? So the first instruction is a load, so we can in the first cycle, in the first instruction, we can schedule the load F0 $R1. What we do next? The second instruction is an add floating point that has a dependency on the first instruction on this load. So we are told that this load takes two cycles to execute. So the add that will execute in the floating point unit will not execute the cycle after, but 2 cycles later. So the add D, I don't put the parameters, but the add D will be here. Next, the instruction the store, which has again a dependency from this add because F4 is computed here.
and we need F4 to store it back. We need to know the latency of the add D, which is 3 cycles, because we are told that all the floating point operation take 3 cycles. So we will execute the store on this unit, of course, and not the next cycle, not 2 cycles later, but 3 cycles later. So the store will be scheduled here. Okay, so this is for the 3 main instructions of the body. Then we have the instructions that sort of govern the advancement of the loop. One is a sub-I that computes the new value of this index or of the address. And we have a couple of dependencies here, right? We have a dependency from the previous R1, which is already at the beginning. So it's an ALU operation, and we could potentially schedule it here from that perspective. But we have a different problem in the sense that we have a read of the old value of R1 that is here, and we're going to write a new value of R1 with this sub-I. So we have a write after read dependency. We are not renaming, and if you think long enough, there is no easy way to rename things in this case. So because this read has to be done before the other write, we need to put the sub-I as late or as early as possible, sorry, in such a way that it doesn't overwrite the R1. The latency is 2 cycles. So actually, the solution is a little bit better than the one I'll show on the slide. The one on the slide is probably a little conservative, because I can put this here. Let's think if it is correct. So this one will produce R1, will not produce R1 here. So R1 is still correct, and this guy can read the old value of R1, and it will be ready here when it has already been read and everything is fine. So this should be the most aggressive scheduling for the sub-I. And then since it takes 2 cycles, we will schedule the dependent operation, which is the branch not equal to 0, based on $R1 for loop in this position. So this is the first instruction, second, third, fourth, fifth, sixth, and 7th instruction. The solution is slightly different than the one that we see on the slide. I wonder why, but I think this is or should be correct.
Okay, we are not very happy then, right? This is better printed the schedule, right? And what we have something where there is almost no parallelism, right? If I look across the different functional units, there is only one instance in the complete program where I have some parallelism, and maybe it's not even terribly critical to be so, right? It could be, it's almost per chance, right? Rest, there is 0 parallelism. Okay, so very bad, right? We are here to do instruction level parallelism. We fail miserably. Now, before we continue, we have to ask ourselves a question. This is a silly example that I invented. So you have the right to ask, actually, you have the duty to ask yourself the following question. Is it that there is no parallelism because there is intrinsically in this piece of code no parallelism, or is it a problem with our new idea of doing VLIW processor? In other words, if I go and give this code, or the original code, right, this code to a good MIPS machine that plays all the tricks that we have seen in the dynamic scheduling part of the course, would I get something as crappy as this, or would I get something better? I would like to be in person to discuss this a little bit together. I have to do here only the little pause where you can think by it yourself. Would you imagine a better execution of this code by a classic superscalar, by your x86 processor that is in your laptop in this moment? It is difficult to give an answer, a quantitative answer to the question whether it will do better, but certainly qualitatively it will do much better than this schedule. Let's try to think of it. And again, maybe all the details are a little under-specified to be sure that what I say makes completely sense, but qualitatively, you'll see where we go. Suppose, for instance, that I have a superscalar that fetches 4 instruction fetches and can issue up to 4 instructions in the per cycle, right? So first cycle, I take the load, add the store and sub-by, and I am essentially in the same situation that I had here, right? I cannot do, I can do the load immediately, I cannot do the add, I cannot do the store. I actually can do this sub-I immediately because since I do register renaming, I can execute it immediately, but it's not going to help much, right? So far, I'm sort of a victim of the same dependence. Then second cycle, I fetch the branch not equal plus a bunch of instructions that I don't see and that are not relevant to our discussion. Now the branch not equal, what do? It's a branch, it's a conditional branch, so I do some prediction and I predict, because I'm lucky, that I go and re-execute the loop because I've seen it before, for instance, and I know that usually I continue the loop. So since I predict it, I don't issue anything because I'm in the same situation that this machine was on the second cycle. The load is not done and everything that was waiting needs to be still waiting. But the point is that I can go and on the third cycle, I can fetch these 4 instructions again. Now I have a second load, which is available, with the R1 that has been incremented because this was executed in the first cycle. So again, don't be too picky on my numbers, on number of cycles, but basically this is much faster to execute. So very soon I will have this R1 available. And now I can issue this second load. So again, let's not be too picky whether it happens on the third cycle, second cycle, fourth cycle. I don't know, and it's not very important. But you see, qualitatively, I am not waiting for the complete loop to execute completely before I start again. I am already starting the second iteration. I overlap different iterations which have one important feature in this in this program. They are independent. Each iteration is independent from the other because of the type of code. I do overlap. So although I don't find any way to go above this dependency or this dependency, what I can do is to break the control dependency, right? Break the control dependency and restart the loop before. And how do I do it is the things that we have seen is this speculative execution, because actually maybe I'm doing a mistake, but if I'm not doing a mistake, I will go much faster. Okay, so I hope this gives you a sense that life is not going to be so easy, right? We were doing better, and now if we are naive, there is nothing that we don't do very good. So the point is that we need to find dependencies, right? The name of the game is all about dependencies. And we have two types of dependencies, as usual: data dependencies, which are these arrows that we see here, right? And control dependencies, the fact that we have these branches and we don't manage to go past the branch unless we speculate. And if we have removed all these beautiful reorder buffers and so on that were the key of our speculation, we cannot speculate. And so how do we get performance in these conditions, right? Here, in this piece of code, but it's only this piece of code, we don't have parallel, we have data dependencies that we cannot do anything about within every iteration, but independence between iterations. And what prevents us to achieve that is control dependencies. In other cases, maybe data dependencies are the major concern. So what we do, we'll start by looking first at control dependencies, what is killing us in this case, and then we'll evolve and continue with data dependencies. So what is that we can do to minimize the problem of control dependencies? How can we handle branches, and especially unpredictable branches, the moment we do not have a speculative execution to save us? So we assume that we have abundant resources because we have this parallel machine with plenty of units that we can control, and we just care for performance. So one of the ideas that we can consider is not to execute one of the paths when we have some ifs, if then else kind of structures, but execute all the paths and make the decision or rely on the decisions at the end on which path was actually to be executed. It's probably easier to explain with an example. Let's take this super simple artificial program where we test for equality A and B, and then we compute something different in C. And suppose that, of course, the computation of the comparison takes time, maybe because A and B are being computed and there are some latency. One of the things that we can do is to rewrite the program in sort of pseudo-assembler. It's not really assembler, but is individual operations in the following way. We compute the outcome of the comparison in a special register, and we use this special register to decide whether the instructions that it is used to annotate with will have to commit the value. So basically, let's read it. C equal 2 times D is a calculation, and then the result goes in C. Of course, not C, but some register, right? That doesn't matter. But the point is, we are going to write in that register only if P1 is true. And P1 is another register, right? So now this instruction, this C equal 2 times D, which is, again, will become a normal instruction, has two data dependencies, right? It has a data dependency on D. If I don't have D, I cannot compute the product. And it has a data dependency on P1. Unless I know P1, I cannot decide whether I write this value into C or not. And you see the second instruction, which is completely dual to this, and is the commitment of the value depends on the opposite value of P1, that is, if it is false. So what is the point of all this? The point of all this is maybe dual, right? On one side, these two instructions, the instruction C equal 2 times D and 3 times D, can be executed in parallel. So if I don't know which one is to be executed, and if I have plenty of units free, I can just essentially try both and figure out, which is in some sense even better than predicting and speculating because I don't need to, right? The second aspect is that, funnily enough, the second version of code doesn't have any branch at all. What used to be a branch is now this data dependency which decides whether to commit the value in the register or not. Now you see how this is funny and powerful, right? This is the reason why this technique, at least in compilers, is called if conversion, because you convert the ifs. The ifs disappear. You have now only data dependencies to schedule as usual in some sense. What you need is this additional support for the ability to put a result in the register only if some flag is true or not. So you need to change something usually in a processor to implement this. This is called predicated execution, and these P values, these flags, if you want, are called predicates or predicate registers. And these things that you need to add are exactly these predicate registers that are special registers that are typically 1 bit each, so very cheap registers maybe. You want instructions to set these predicates, not very different if you know, for instance, x86, there are plenty of instructions to set flags. Is essentially the same thing, except that the flag is named and is a register. If you know MIPS, you know the set lower than, or these kind of instructions that set a register to all zeros or all ones. But again, it's exactly the same thing, except that you have the same instruction, but only for this 1 bit register. And finally, you need to have this ability to add into maybe any instruction, like in our case, a bool instruction, one additional parameter or multiple additional parameters that say, actually typically is one, that says, do it only if this predicate, specific predicate, which is a new operand, is either true or false. Right? There are some issues, as usual, with exceptions, because you should not have an exception on a path that is not for really being executed, but I think we'll see something along these lines a little later today or next week. Okay, so if we do this, if we have this possibility, what we are doing, what we achieve is, again, this if conversion, this transforming control dependencies into data dependence. And what is the importance of that? Well, it's one of the leitmotifs of this VLIW compilation, is to be able to schedule better. Why do I schedule better? Well, I hope that the figure starts suggesting the idea, right? Because I have plenty of basic blocks, all these boxes are basic blocks, right? Where there is decision. So basic blocks are sets of instructions that when one is executed, all of them are executed. So there are no branches in between, and the branches are at the end to connect the different parts. If I have to schedule each of these individually, maybe I will be in the same problem that I had at the very beginning, right? Remember when we, our little example, we had these 3 instructions to schedule in this basic block, 5, but 3 were the kernel of the computation, and it was extremely difficult, and it was impossible to do a packed schedule because there was not much stuff, right? So this is the situation that we may have into each of these basic blocks. But thanks to this predicated execution, what we achieve is the fact that all these individual basic blocks, and I can do it recursively, right? You see P1 and P2 and more if needed. All these predicated instructions now belong to a single huge basic block. Why does it matter? Well, because I will be able, most likely, not guaranteed, but most likely to have more chances for parallelism. Actually, in some cases, it's almost guaranteed, right? Because these two parts, by constructions, are independent, right? The then and the else cannot have a dependency between them because they are not supposed to be executing at the same time. And so the hope is that making basic blocks bigger by this technique, I will have chances to do better. So practically every VLIW processor in history and in reality today has predicated execution because it's one of the very essential means to take away from my code this little then and else that we write all the time, right? Imagine, take your last program that you wrote, and you certainly have plenty of examples of these little then else, and make them disappear so that they don't become a major jeopardy to the performance. In fact, it works so well that some processors like ARM, nonetheless, the sort of one of the top RISC processors in terms of usage and popularity, has all instructions that can be executed conditionally. They're not conditional on predicate registers. There are no predicate registers, but there are flags. So whenever you do a comparison, a bunch of flags get set, or when you do every computational instruction, depending on what it is, it may set some of the flags. And then any instruction that you have can say, if the flag is 0, do this, right? And again, the if is inside the instruction. Essentially is do it and then commit it to the register if the flag is positive. Going back to this, because it's a leitmotif that will come back also later, but it's useful to start observing it here. The moment we do this this modification, this transformation of my code, right? I had a code like on the left. This is literally, almost literally what came from the original program written by the user, and I transform it to get this on the right. Every time that I do this, I start having questions, though. For instance, the question here is, do I do it always? Do I do it every time that I have a choice, or at least a converging choice where things go back together? Do I do it for P1? Do I do it for P2? Do I do it for both? It's not a silly question to ask, right? Because of course there are cases like my example where it is absolutely self-evident that is a good idea because I do expose some parallelism in these basic blocks, but it may not be a good idea in some cases, and I'm tempted to ask you if you can think of a case where this is not a good idea. So when is not a good idea to do predication? Well, you can imagine, right? Suppose that these let's imagine simply also this case, and I have these two basic blocks. And imagine that these two basic blocks are pretty big, right? Very consequential, not 2-3 instructions, right? So my argument is that I can schedule better, I can do more parallelism. But what we should not forget is that we are doing more parallelism, so doing things better, but we are also wasting half of the resources, right? And so if these are very big, intuitively, there will be a level when they are sufficiently big that it makes no sense, because instead of taking a, let's say, little problem in performance because I have to take a decision and wait a few cycles for this decision to be taken, now I may be wasting a huge amount of cycles because I'm doing plenty of work that I should not be doing. I'm doing twice the amount of work that I have to do. If it is 50 cycles to do one of the sides of the branch, and I'm doing twice as much, and if it is very dense in the sense that I cannot parallelize it more than some, this is maybe much worse than waiting the 3 cycles and finally doing only the right job. So the problem is, how do we decide? Well, it depends, right? If you followed me in my rambling about is it good or not good, 50 instructions and so on, you understand that there is a lot into this question, right? It depends. It depends if the 2 sides parallelize well because I have enough units, or if not, if the one individually parallelizes particularly poorly, then maybe there is space for doing the other side and of the if then else, and it costs me nothing. But if one of them packs very densely because there are not many dependencies in the then when I have the else, well, I don't find any space, so I need to lengthen my schedule, right? So there are a lot of considerations that come into figuring out whether it is good or not. And this is one of the problems of VLIW compilation, is that these decisions are hard, right? And they are all over the place because there is there is a branch all over my programs. So every time, if I have to figure out what is the right decision, and this decision depends on how good scheduling can be, well, you can imagine, right? It's very hard. Or I make it easier and I take some heuristic and I say, well, I will only apply predication if, I don't know, the then and the else are smaller than 5 instructions, which seems a reasonable heuristic. I'm not saying anything about the 5, but some size, right, makes sense. But then maybe I lose in some critical cases some advantage of the predication and I take a hit in performance, right? So this is one part of the story, right? That we have some ideas, but then it's very difficult to apply them. And we'll come back to problems like this later. Coming back to our predication, I just wanted to give you one example that you can follow yourself here, where we do predication without architectural support. Typically, predication is something that wants architectural support, and architectural support once more means having special registers and having this ability to tell this instruction execute it only or commit it only if some predicate is true or false. If you don't have it, usually you don't do predication, but I wanted to show you that even in C, you can write something that amounts to predication. So I let you read it and play around with the code. And there is a totally artificial example of latencies and cost of instruction in a sufficiently simple processor to show that in some cases there may be an advantage even in a normal processor to do predication without the support, the architectural support available. It's probably a special case, but it may happen. All right, that is the first thing that we have seen, a form of how to handle control and how not to be too damaged by control. And if you want, it was a radical decision, a radical idea, because it says, let's remove control, right? Which is not something that you can do all the time. One of the cases where you definitely cannot do what we have just seen is that when you have loops, right? And again, loops are very important situations where there is goes a lot of my of the cost of execution. And so people have come up with a number of techniques to manipulate loops, to modify something of the loops. There are techniques like this that is called loop peeling usually, that says, okay, if you are doing a loop for a given number of times, maybe you can peel off, that is, you can remove some of the the iterations so that you have a different number of iterations. Why would that be a good idea? Well, a priori, never. Why would you do that? Well, there is a reason. You may have different loops that have different number of iterations, but if you do this peeling off some of the iterations from one of the two loops become compatible, so to speak, in terms of iteration, and they can be brought together. You have here an example, of course, pretty artificial, but is not unthinkable that this happens in practice, and it does happen in practice, at least in some types of code, where you have two loops that do things almost identically, but not quite in terms of iterators, but have a completely different content. And the beauty of this is that by peeling off two iterations of one of the loops that become a little bit less efficient, because now you have to write explicitly these two iterations. So in a sense, they are a bit inelegant. But what is very nice is that by fusing the two loops that now are compatible, what you have inside are two parts that are completely independent. And then again, you see this notion of making the basic block that is here at the body of the loop bigger, right? Instead of having two relatively little basic blocks and two loops that are characterized by these small kernels, you have a larger kernel with more potential for parallelism. So there are a lot of games of that sort. You can also split the sum if you have some dependencies, because one has a loop carried dependency and the other not, and so you can do transformations because maybe you can connect it to the other, things like this. The king of this transformation, and the one that is really aimed exclusively to the purpose of having larger loop bodies and basic blocks in the loop body, is unroll. And I guess you are familiar at least with the idea, right? That the idea is that literally you repeat the body of your loop many times. You make adaptations that you need to the indices, and then what you have here is a bigger body. And of course, you have to execute if you have unrolled by a factor 4 times less times the loop. Now, why does it happen? Why does it help? Is the normal answer, right? Is because I have a bigger basic block, I may have more chances to extract parallelism. And the best way to prove this to ourselves is to go back to our example, our disastrous example, where there is this loop that needs to be repeated a number of times, and see what we can do in this case, right? It was a disaster because there was zero parallelism. Now what we want to do is to repeat this loop, unroll the loop by repeating the body a number of times. In this case, 5 is a weird number, but it's also good to remind ourselves that it doesn't have to be a power of 2, even if for some reason people tend to do it mostly on power of 2. Here I do it on 5, I repeat it 5 times. What do I need to do? Okay, replicate the body first. I need to update the references, right? Like in the example that we have seen in sort of high-level language before. And finally, I need to do something that is not essential, but is essential to unleash the potential of this, which is change the name of the register, right? Remember renaming registers, right? I have here F0. Naturally, I would have here F0. I have a write after write dependency and a read, a write after read dependency here. So I could not schedule this load before the add because they conflict by name. So it's the problem that we know super well. It's what we do with this register renaming, dynamical register renaming in our processor out of order processors. What we need to do here is to rename statically, right? Change the name. I use a different register that I didn't use here for the second, the third, the fourth, and the fifth iteration. And now there are no fake dependencies in there. I essentially re-register allocate this piece of code. And now I have this body which I can schedule freely, right? Freely, but with a lot more choice than I had before. And if you do the little exercise, what you get is this, which is much more interesting, right? We are back in business. I remember also the comparison with the superscalar, where we were imagining that in the second, third cycle, maybe another load of the second iteration would be scheduled. It is exactly what we are doing here, right? What we are doing here is that here we are scheduling the load of the second iteration. The way we are doing it is a bit more, I don't know, explicit, trivial. We just repeated the body many times, right? So it works. You see here some silly calculation that it's enough to bring a factor 3 in speed up, which is not negligible. Okay, so one of the things that we should notice from this is that, okay, first of all, we finally achieved parallelism and we managed to get closer to the kind of objective that we had, but we have increased the code. And this increase is not anymore like we were discussing before, because we have these knobs. Yes, we do have here the new version of the code that has a lot of knobs, but even if I forget about this 50% or so of knobs, I still have something like 40 divided by 2, 20 words to encode that make my program instead of 5. So you see the problem, right? In terms of pressure on my cache, my code is bigger, and my code is fundamentally bigger in ways that I can't avoid. Well, that's actually something that we want to see, because maybe there are ways to avoid. So after people have realized the importance of loop unrolling to expose performance in VLIWs, people started looking at how to achieve essentially the same, and we see that it is conceptually the same mechanism of overlapping different iterations and scheduling instructions from different iterations, but in a different way, in a fundamentally different way. And this is the idea that is behind software pipelining, that is probably best explained once more with an example that gives a visual intuition of the idea. So let's take this example, and the example is in fact always a bit the same, right? It's a vector. It's from one vector to another, but it doesn't matter. So I'm reading a vector, I'm adding a constant to all the elements of the vector, and I'm saving the vector. Again, the functionality is not very important. It's just to have something relatively simple with this kind of dependence, right? And this is exactly the problem we had before, where we have a chain of dependencies, right? I know I load, I need to wait to do the add, I need to wait to do the store, right? This is what is important, and this is what is tough, right? If I didn't have dependencies here, everything will be fine because I will do this in parallel. So that's the situation. So let's imagine that we execute this, and this vertical axis here going down is time that passes, right? So first iteration, I execute this part, and then I execute the second instruction, then I execute the third instruction. And they have to be one after the other because of this dependence. What I want to do ideally is that as soon as I'm doing here something else, the add, I use my load unit to load the next value, right? Essentially is what we were doing. I want to go back a few instructions here. Latencies were a little bit different in this case, but while I do the load and I'm waiting and I'm doing the add, I have the load empty. So what I'm doing is I'm doing the loads of the next iteration, right? Exactly the same thing, right? That's what I want to do, and I want to do it on a systematic basis, right? So somehow I would like to have this schedule of execution. And remember always, right? We are interested in schedules now because we have to write the schedule. It's the compiler that has to write the schedule. But if I stare long enough to this schedule, to this ideal schedule of execution, I can sort of read it in a different way. I can think, forget about what happens at the beginning and what happens at the end. What happens is that from some iteration onward, from some cycle onward, what I'm doing is that I'm doing the same thing over and over, which is called, again, an iterator, right? Another loop, but is a different loop somehow. Is a loop made of the same ingredients of the original loop, but somehow differently organized. I hope you see what it means and what it means graphically, right? Here I had a load, an add, and a store of the same of the same iteration. What I have here, the new loop that I want to execute, is done by a store of a first iteration, an add of the next iteration, here is I plus 1, and of the load of 2 iterations later, that is I plus 2. So these are the 3 instructions that I have in here in this body of my new loop. Now the beauty is, which is what I expect because that's why I did it, is that these 3 are independent because they belong to different iterations, right? I'm reading one element of one vector. Sorry, I'm storing one element of a vector. I'm doing an operation and I am storing and I'm loading from yet another vector, right? And another element of the vector. So since there is independence, all these can be done perfectly well and can be scheduled perfectly well. I have a couple of problems before and after because I have these leftovers before and after the loop, right? So let's see a little bit more in detail. It's difficult to go and correct every detail, so you have to trust me a little or spend some time and stare at the example yourself a little later. But let's get the intuition of what does that mean on our example now, right? Remember, again, the idea of unrolling the loop, and let's sort of do it. And let's use this to sort of see here that we have a part that becomes regular, right? Here there are some things that are yet irregular because I haven't started doing the store. Here they are irregular because I'm not doing loads anymore because the loop is finished. But I have a regular part in the middle. So the solution is this one. Why the body contains 3 loads instead of a single load, right? If you go back to my example, qualitative example here, there is here a single load. The 3 instructions here are 3 instructions also in the, sorry, the 3 instructions not here, the 3 instructions in the original loop are the same 3 instructions that are in the modified and reorganized loop. Here things are not so beautiful because I have 3 loads, 3 stores, and 3 adds in the rewritten loop. So the loop is not as compact as it could have been. The body is not as compact as it could have been. You have to think about it for a minute to understand exactly why. The intuition is that it has to do with the longest latency that you have within a loop. In this case, it has to do with the fact that the floating point add takes 3 cycles, and you need to have 3 bodies, 3 replicas of the body in the new restructured body. And if you had latencies 1, it would be as perfect as my qualitative example at the very beginning. So They are just technicalities. Again, you can go back a little bit and try to understand this more in detail. It's difficult to go here and analyze, but you basically see that you are writing F4 here. You need the 3 cycles to get this value, so you need to find something to do until you can restart the loop, and now the F4 is ready to store, right? So there is a dependence between this one and this one, but you need to fill your time. How do you fill your time during this a few cycles? Well, you put more iterations in the body. But you see that when I do this and I do only 3 iterations in my body, not 8, not 16, not more than that, I have an incredibly well-packed body. And then I have all this dust, leftovers before and after. So I achieve essentially the same result that I achieved by simply unrolling, but I have a much smaller and tighter body. Imagine always that this is a much longer iterations, right? Sort of, and therefore, if I have a gazillion of iterations, I have unrolled only a little. I have the code that is only a little longer, but the body is extremely compact and relatively short. So what I need to put in the cache to re-execute is very short. If you go back to the example as it was before, the loop itself was much longer and made of 13, 14 instructions, very long instructions, and therefore the occupancy of the cache, the space taken in the cache was much longer, and the chances that I could fit it in the cache were much lower. Okay, so just a comment on the name, right? It reminds us, it's called software pipelining because it reminds us of what we've done for instructions already, where we had different pieces of the instruction that were advancing in parallel. Now what we are making advance in parallel are different iterations. So it's exactly the same idea, but obtained in a completely different context, right? You see how pipelining is useful. We're not doing hardware anymore. We're not adding registers anymore or doing things like that. We are just restructuring code to get parallelism. We have seen a couple of techniques for handling control flow decisions in an efficient way. The first was this idea of predication. I may not have said it, but I guess it was relatively self-evident that it's something to handle decisions like if then else in cases essentially where the decision is relatively unpredictable, or it's relatively balanced, but sometimes I go in the then, sometimes I go in the else, but there is no strongly dominating decision. Why? Well, because I'm executing both, right? And so if I were sure to execute in 99% of the times one of the two, maybe I could do a bit better, and this is exactly where we are coming. The second thing that we have seen is this idea of handling loops, loops being one of the sort of important paradigms, schemes in our programs, and therefore being pretty critical for performance. And we have seen all these, on one side, techniques to split, join, combine loops in such a way as to get the largest kernel and the largest basic block internal to the loop, so that we can have more chances to schedule well, plus the sort of king of the transformation in this respect, which is the idea of unrolling this the loop and replicating several iterations, sort of creating new iterations composed of several iterations of the original loop. We have seen, and it belonged to the same category, smarter way to achieve essentially the same, like this this software pipelining. And now comes the question to say to the third maybe category or question is what to do of those branches that can be reasonably well predicted, or more than predicted, they tend to have a very dominant outcome. Can we do better than doing predication? For instance, in the case that also the code is more significant in the than and else, and therefore predication is not a great idea. And here is the idea, again, suggested with an example that is a relatively sort of silly example, but gives you a bit the idea. Is suppose that you have this program, you have an if then else, and you typically take this part. And you would like to do things faster. And again, think faster means I want to have bigger basic blocks, because bigger basic block gives me more chances of good scheduling. And so one thing that you could do is this, right? You could say, okay, let's move this operation that was here in the basic block that precedes, so in the basic block that is executed anyway. It's okay because I know that in most cases I'm going to do it. And if I'm wrong, if I'm in one of those situations where I should not have done it, I will do something additional, some cost, I'll incur some cost to compensate and to annihilate somehow what I've done and I should not have done. I think it's already time to ask ourselves, what is this? And I hope the answer is immediately clear to all of you, right? This is a form of speculation. I am executing something that I should execute in 95% of the cases. I'm executing it anyway because I think it makes sense. And I have a price to pay if I misspeculated. If my speculation, if my guess was wrong, I'm going to do something else. You notice the difference, right? This is static speculation, it's not dynamic speculation. It's not that I go down one path and come back and execute the other path, as we discussed until last week or a couple of weeks ago. What we are doing here is rewriting the code so that in the code there is this notion of speculation, but actually there is not written anywhere, there is nothing in the code that really says speculation. It's just that I refactor my code in such a way that effectively it does speculation. So it's essentially to achieve the same result that we were achieving with prediction and speculation, where here prediction is someone has to tell me about this 95% and 5%, because of course otherwise I have no idea. And once I have this prediction, I do speculation by modifying my code statically and giving to the machine some code that, if this prediction was correct, will be more efficient. Oh, where do I get the 95% and the 5%? Here is one of the things that are typical of VLIW compilers and maybe also typical of what people don't like of VLIW compilers. I need profiling, right? That there is nothing else that I can do than have this information at compile time. Who can give it to me at compile time? Maybe the user, but it seems very unlikely that the user wants to give this information and is not even sure that the user has this information. And so the only thing that I can do is to try to run the program, non-optimized, essentially this program that is bad in terms of performance, but doesn't matter. I try to run it on some benchmark or some representative data sets, and representative is the key word. Maybe they are not, right? I don't know, but I'll run it on something. and I get the profiling statistics, that is the fact that these branches were taken so many times, and then I build my code assuming that for all data sets this will be true. And you can imagine easily cases where it's hard that to have this information or to believe that this information is true in every case, but maybe in many situations is actually okay. All right, so this is a bad idea. Sorry, just to stay on this slide for a minute more. This is a bad idea, right? You don't want to do this. For instance, if X is a float, this is a horribly bad idea because since a floating point is non-associative, I cannot add 5 and take away 5 like if nothing happened, because maybe the result is not the same anymore. You know perfectly well these things, I suppose, but the point is that you don't need to do this. This is just the idea. You can reformulate the same thing in an arbitrary form, where essentially you put in a different register or a different name, different variable, the speculative calculation, and you overwrite the speculative computation with the original value in case the speculation was misspeculated, was wrong, right? So it's perfectly fine. This is a very generic technique. And in this form, this is what one of the big proponents of VLIW, Josh Fisher, introduced in 1981. By the way, you notice the year, right? It's before one will do out of order, heavily out of order computation in general purpose computers. So this idea has been around for a long time and has been refined fairly slowly over time to try to get it to work. The idea of trace scheduling is to do it recursively, right? And so you start taking the most, the sequence of the basic blocks that you follow more, that you are more likely to follow. So it's not just about speculating this simple branch, but all the different paths, and you put together essentially all the basic blocks. It becomes a super basic block. This trace becomes a large basic block, and then you jump into the rest of the code whenever it didn't work properly, right? You didn't do it well. So the rest is the rest plus the compensation code that you need to undo whatever you may have done and that was not to be done. I said this already, right? This is a form of static speculation. And again, the goal of it is to do scheduling on a larger basic block. So instead, or on larger regions instead of basic block. Basically, you try to do the scheduling across basic blocks. Is just maybe a naming convention, right? What do you call this? Is either a new big basic blocks, or you call it a region, because in fact maybe you are coming out in the middle of the region, so technically it's not exactly a basic block. Again, they are details, they are not important. I hope the basic idea is there, right? You want to bring things together so that you have more choice in the scheduling phase to find things that are data independent, and you can do a better schedule with more parallels. This we said already. How do you do? We have seen it, right? Is with this I1 in the second slide when we were here, right? How do you do it? You essentially use a renaming. You use additional registers to hold the speculated or the pre-speculation value, whatever. So you duplicate the content in the machine until you resolve and you keep and you take the right one. right? Sort of this means that you have additional names. One of the problems that you are going to incur is exceptions, right? Why do you have problems with exceptions? Because you are moving code that was here, and is exactly the same thing that we were discussing some weeks ago. I don't remember how many, when we were executing something before knowing if it has to be executed. And if this something may create an exception, we have a problem, right? Because the user did not say that we have to do it, but maybe we were going here, and if an exception comes here, it should not, because nobody said to execute that. If I put it here, if I don't take any precautions, the exception will happen, and it's just my compiler that made a mistake because it created code that raises an exception when there is absolutely no reason for that exception to be raised. So this has to be taken into account. We will come back to this when we'll discuss a bit how Intel handled this in the Itanium processor. But is similar to what we discussed already when we were talking of speculative execution. So here is a table that gives you a sense of the different things that we know how to do and how we do in superscalars and how you do it in VLIWs. And some of the things don't ask for anything or much in the architecture, but some of the things need something in the architecture. And once more, we'll come back this later, talking of the Itanium to understand exactly what is there to be done. Again, the problem are exceptions. There are a few slides that I don't think I want to spend too much time. They just give you a sense of what the movement of instructions across basic blocks you can or you want to do, and how much corrections you need to implement. For instance, if you move an instruction across an entry into a region, you will have to replicate this instruction across the side entrance in the region to maintain the semantic correctness, right? And there are a number of transformations. There is nothing particularly important or fundamental here. The point is, people have developed tools, conceptual tools, methods and schemes to handle all these transformations, so that by doing a set of transformation of this sort, you get code that remains, of course, semantically correct, but creates increasingly large regions that can be scheduled efficiently and for the best result. One of the notions that became important at some point, because it has some theoretical advantages in doing this, is the notion of superblock, which is a specific type of trace of sequence of basic block that doesn't have a side entrance, but has only side exit. And that contains, actually that is maybe the hyperblock, doesn't matter, that contains also predicated region. So it's not very important, the details of that. What I care here is that you get a sense of what are the type of transformations that one can do and the type of games that one can play to get these things. Of course, if you need to do it, there are plenty of books and papers that need to be read properly. Okay, so this completes what we wanted to look for control. And again, if I do a little summary again, maybe changing the order, we have handled more or less everything that we need, right? Loops, to try to make them more efficient by making bigger blocks. bigger basic blocks. We have seen what to do in case of branches that is appropriate to speculate because they tend to have a very distinctive tendency to go one way or another, and so we try to move instructions across the branch to execute them speculatively and execute them in more well schedulable context. And we have taken, we have looked at a technique, a predication that needs actually some hardware support, but which helps in the case of poorly predictable branches. We want to look now at the other facet of things, data dependencies, right? Instead of control dependencies, how to handle data dependencies. And data dependencies, there is not a huge lot that one can do, right? We know all these stories. There are the read after writes. These are the true dependencies. There are the name dependencies. Name dependencies, in some sense, don't exist the moment we do the job properly, which is use more registers. They are just an artifact of the fact that I have a limited number of registers. So if I have a lot of registers, I can avoid them. Think back to one example that we have seen before, where I may not have made the observation. When we did the unrolling, right, I did say, well, we need to rename the registers. It's not actually a need in a strict sense. We can not rename, but then our ability to schedule will be reduced by these name conflicts. So we want to rename so that we can schedule really freely. This is true everywhere, right? We don't want to have to be limited by registers and to create scheduling constraints by the number of registers, but that also means that we need more resources. We will need processors with a lot of registers. You have certainly in your head the classic numbers of 32 registers for typical architectures like MIPS, and in practice, not very different for x86. Itanium, so when you want to do a VLIW, it turns out that has, for instance, 128 registers. And this is significantly more, is even twice as many registers as the MIPS R10000 has, if you also count the rename register. So somehow the pressure on registers is significantly increased in VLIW processors. So what can you do about dependencies? I don't think you can go through these slides. I don't think there is a lot of things to be said, because basically dependencies you have to obey. And essentially, you know, you can find very easily these dependencies because they are clearly written in the code. It was our actually initial motivation to do VLIWs, is to say, okay, come on, there is a dependency, I see it, why do I have to discover the dependency through the hardware at the last minute? Now, there is another part of this, which is dependencies that are not through the registers, but are data dependencies through memory. So the case like this, it's completely invented, of course, but I have a store and I have a load. The load comes after, and of course I want to anticipate the load, right? Because the load is the one that is creating a data dependency, right? I put in some value in F0, and arguably someone needs this value that is in F0, and I want to do and I want to have it as fast as possible so that I can do and schedule other operations. So I want to bring this load before the store, and the question is whether I can or I cannot. Remember that we are in a compiler, right? We are looking at this at compile time, so I don't know what is the value of R0 and R1. So this is one of the things that are easy at runtime. Maybe they take some time because I need to wait for R0 and R1 to be computed, but eventually they will. And so the moment they are computed, I can decide whether the load can go above the store. Remember again, we have seen this case and slightly discussed it with respect to the reorder buffer, and we said actually more than a reorder buffer is a second reorder buffer, that is this load store queue that does all this specialized reordering. That was exactly the functionality, right? Understand if a load has some outstanding store before it, and if one of these outstanding stores is conflicting, I cannot execute the load before, but if there is no conflict, I can. So this I can do if I am doing, at runtime, I am trying to detect these things. What can I do at compile time? So one of the things that you can, it's one of those areas where you can say, yes, okay, I don't know anything about R0 and R1, but R0 and R1 are computed by me, by my program that I have here. So maybe I can stare long enough, or I can do analysis through my compilers on the code to learn something about this R0 and R1 that will tell me whether there is certainly, there is never, or there is possibly a collision between these two addresses. You can take this example, which is a completely manufactured synthetic example for the purpose of the course, but get a sense of the kind of situation, right? I have here a write before, right, a store at one address, and then I have a load at some other address in this data structure. And the question that you would like your compiler to answer is whether there can be a collision, this address, A plus J size of A, right? These kind of things that you do in C. This address and the address computed because of this can be the same. And for instance, in this case, it's easy to see, that's why it is sort of manufactured so that we can all see it. There is no dependency because there cannot be any dependency by construction, because this is always an odd number, this is always an even number because of this. So the result is that there, again, cannot be any collision, they cannot be ever the same index. And so it is a very favorable case where I could exchange. Now, solving this and understanding this is extremely costly, is mathematically extremely costly. There are techniques, there is all a theory of polyhedral analysis that does this. There are libraries that you can use. The libraries are actually very commonly used because it's a problem that comes out in different contexts, in different situations. We'll come back to this a bit later when we will discuss high-level synthesis, because we have the same problems there. But the point is, there are situations where this analysis brings something. If you have relatively regular kind of situations, a fine addressing, a bit like here you have, that you have some hope to detect and discover things. But in the general case, imagine you are going down a data structures and you have pointers and you want to know if these pointers point to the same substructure, whether you have absolutely no hope to find out anything. And if you have a situation like that, of course, you need to be conservative, right? You need to assume that there is a dependency and keep scheduling the load after the store, and you cannot change the order. Now, you'll see that there are, so first of all, this is extremely bad, right? The moment I am in the situations, the favorable affine calculation situation where I can tell something fine, it's great, but unfortunately it's not very common. The moment I am in completely general purpose situations where I have arbitrary data structures with pointers that can alias in every possible case, this is a disaster, right? Because it's really preventing my good scheduling, because I have to keep this load after the store, as I say, and this is a strong limitation in the parallelism that I can exploit. So we'll see later that there are some techniques to handle this, because it's so bad that we need to do something, but we need to have, again, some support in the hardware for doing this speculation. So it's not going to be a simple trick. Okay, so we're getting to the end of this part. We're going now to spend some time to study one case of this VLIW processor, which is Itanium by Intel, but we're then looking at the compilation techniques. It's not a course on compilation that I want to give here, and there is no way that we can cover that matter, and it's actually pointless. The only goal that I have in this part is to give you a sense of how many different problems accumulate when you want to do in the compiler what relatively naturally your superscalar processor does it by itself. And there is one part that I want to insist on, because we'll also come back on this later, is that it's not so much that we don't have techniques to do the right thing in the right case. The difficulty is maybe more, we don't know what is, among all the things that I can do, which one is the right one to do in a specific case. This is very often the difficulty here, right? The space, it's actually a combinational problem, right? A combinatorial problem. Like, I can do a gazillion of different transformations of my program. Some are completely stupid, but some combination of very strange optimizations may lead to a code that is actually very efficient. But which one? How do I find out? And it's extremely hard, right? It's extremely hard, it's extremely time consuming. You all have compiled programs, and you all have been unhappy of how long it took for GCC to recompile the program. Now imagine that the problems to solve are 10, 100 times more difficult, and therefore it takes 10, 100 times more time to get the code out, and you'll see how unhappy you may be. So building compilers for VLIW is intrinsically a very hard job. People have been trying for a long time to prove that you can do it. You can in most cases, or at least in some important cases, but it's very hard to build. I will go to the point of saying, if you're doing GCC for x86 and you do reasonable choices, it's hard to make fundamentally wrong choices, fundamentally bad code. You'll do code that could have been done better, because there could have been some choices that were hard that could have been done better, but it's not going to change dramatically the performance. In some sense, it's easier to do that. It's easy to do that kind of compiler. When you do this kind of compilers, unless you do the one or few combinations of transformations that really make the code right, you have an extremely bad performance. So that's what makes this really hard. So to conclude this part, what we want to do is to spend some time in looking at maybe the only real incarnation of a VLIW processor for the general purpose world. I come back to this point later of what are the real implementations of VLIWs, but this is the only one that has been done in the intent, which was surprised everybody in the world, of replacing somehow or addressing the same type of applications and use cases of our x86. So it was a funny story that you may want to go and check on Wikipedia for the curiosity on how things went. But essentially what Intel did at some point was to say, okay, we have done, you probably know a bit of the history of the x86 family, right? That they started at actually 8 bits because there was the 8080, 8085, then they did the 8086, 16 bits, then 286, and so on. And so they continued to increase the data width of the processor up to 32 bits with the various Pentium members of the Pentium family. And then they said someday, and everybody has been following this, right? So it was the instruction set that was modified in compatible, backward compatible ways to accommodate larger bit. And then they said, okay, but we are not going to do a 64-bit version of this. No way. The 64 bits that we are going to do is a completely different architecture that is called Itanium and is based on this great idea of explicit parallel instruction computing, or VLIW for the rest of the world. It was a very, very strange decision that took everybody sort of by surprise. And at the time it was called, actually it's no longer called IA64, as in Intel Architecture 64. So the x86 at the time, for some time, went under the name of IA32, the 32-bit Intel architecture. And forget about that. When we go to 64, it will be something completely different. It was one of the biggest blunder of the history of computing. And it's amazing that it has been made, and sort of is a decision that has been taken by the company that had already an almost universal recognition and market positioning determined on binary compatibility. And they said, okay, we'll do something that is binary incompatible, bear with us, it's going to be great, right? Which is funny, right? Because they killed basically every other competitor because binary compatibility appeared to be so important. Anyway, so again, it's a funny story, but what is interesting here to us and for the course is that this is a real problem, processor. And why is that matter? Is that there is a huge difference, I believe, between people that write academic papers. It's not that I don't like academic papers, right? It's my job. But between me saying and arguing in a paper that is a good idea and look at the cute idea that we can use and investing money to make it competitive with the top processor of the times, is a big difference. So it's actually very interesting to see what it takes to be competitive with the best processor of the standard category of the superscalar world. So we can learn something. So let me go through a few of these slides. I'll skip a few, you can look at them. At the same time, you'll study some of these because of the second homework. So no big deal, but let me go through a few things so that we find back some of the basic ideas that we have discussed in general. So here it is, the very long instruction word that is not exactly in the form of the very long instruction word that we have seen at the beginning, because they have these bundles, right? You have here the 3 instructions, so 3 instruction in the bundle. So this then is the very long instruction word, and these are what I tend to call more like operations. And they have this template. What is the template? The template says what are the type of the 3 instructions that I'm in, right? For instance, I have this one here. It's an MII, which means that there is, I'm surprised. Let's take this one because there must be something that I forget now. But this is MMI. It means that there are 2 instructions that are of memory type and 1 of integer time. And here is load store, and this is some integer type, which is actually setting some predicate registers. And there is a possibility to decide where is the end of the cycle. So think about it for a second. What is this? This is a specific form of the encoding that we discussed at the very beginning to avoid the knobs, right? I remember the idea of steering, of saying where each instruction has to go. Well, it's said here. It doesn't say exactly to which memory unit it has to go, but it underspecifies it by saying one of the memory units. And I will guarantee myself that there is at least one free. So the processor has dynamically to find out which one. And I'm telling when there is a stop, right? I mentioned this sort of stop bit between cycles. These two things that are in red here are encoded in the templates, in these 5 bits. Now it's not a complete encoding because 5 bits are not enough to say all the combinations, but basically there are some templates that define different deliveries where the instruction should go and stop bits in different combinations that are enough to use. And if you cannot use it, you basically put probably knobs or something like this in some of the slots to make it fit. It has predication, so I'm not going to stay on this too much. It's exactly the kind of things that we discussed, but it's a bit more complicated in the implementation or rich in the implementation than what we have seen. This is the simple version that we have seen. There is not P1 and not P1, is actually assigning using two predicates for the equality for the positive test and the negative test, and so it is two different predicates rather than a negate of the predicate. That is a detail. But what is more interesting is that you can do things like this, which are a bit surprising maybe. Why? Let's read it. Let's try to see what it is. What we say is that we do a comparison for equality between two values, and we set P1. But the funny thing is that we do plenty of them in parallel. You see here, there is the end of the cycle. So it means that these 4 instructions, the 3 compare and the T-bit, are done at the same time. They are part of a very long instruction word executed at the same time. And there is a condition or in between them. It's exactly what you wrote, what you see here in the original code is P1 will be set here if A is equal to 0 or I think 0 is larger than or equal T, and so on and so forth. So there is a dependency that is between these, right? Because this is the OR of the previous value of the P1. So it's a very strange situation somehow because you have an internal dependency. So you are breaking to do this cute thing. You're breaking actually one fundamental point, that is, we said is explicit parallel instruction set, so this can be executed in parallel. It's not true anymore, right? They are executed partially in parallel. This is certainly parallel, but this chain of OR is not parallel at all, except that it's probably fast enough that I can implement it in hardware, and so it's okay. So you see that we start making, we wanted to have something extremely clean, but then we start putting in strange things that are probably there for efficiency, right? Of course, this is a very nice thing that you can do, that you compute a multiple condition all in parallel, but it has a cost both in elegance, which matters, and in implementation. Another thing that is sort of funny to to be able to do, maybe less surprising and less problematic in the implementation, is that you can do the following, right? You can compute in a cycle plenty of different conditions and then perform the different branches with different different predicates. Now, of course, what do you do if both of P1 and P2 are true? Do you branch to both? Of course, it doesn't make any sense. And here comes the fact that I said something sort of silly a minute ago. This is not less surprising than this one. It's again a case where I have something that is supposedly perfectly parallel, but in fact is not perfectly parallel, right? There is a dependence. I go and do this second if only if the first if resulted in an else, it was not true, right? So there is a chain dependency between instructions that in principle will be parallel, right? So again, we are making compromises, but of course we're making it possible to be more efficient. One of the things that I like to mention in this is that the hardware does, the Itanium has everything in terms of branch prediction. So it has both static branch predictions, essentially hints from the compiler. The compiler suggests whether this branch is probably always taken, never taken, and so on and so forth, with a lot of even nitty-gritty stuff that is very difficult to use by hand. Actually, it's not meant to be used by hand, but meant to be used by the compiler to suggest or request some housekeeping, if you want, in the predictors, right? So normally you assume that the predictor is something that you absolutely have nothing to do with, right? The predictor is there, you have branches, and the branches get predicted, and the predictor learns and changes and so on. And here you have things to help the predictor. And on top of this, you have hardware support. Among the most, at the time, I think, of the conception of Itanium, it was one of the most complex prediction support in hardware, because there were even different prediction schemes, and there was some sort of competition between the prediction schemes. So you will not only make different predictions, but try to predict which one of the predictors is a good predictor. It gives you a sense of how things are critical, right? You don't do these things because you like them and because they are elegant or because they are funny. You do these because you need it, right? And what you can imagine is that if you do a wrong fetch and decode and so on and so forth, you don't do speculative execution, but you will bring in the pipeline instructions that are potentially wrong if you mispredict. You can imagine that it is particularly bad in this processor, right? Because you bring in a lot of parallel instructions and so on, and so you just need to empty the pipeline of a number of things. So you don't want to mispredict, and that's why you probably are particularly picky in making your predictions well. Here is one of the examples that we have seen already when we were discussing speculation, right? So again, control, how to handle control well. And it's the case of a load that happens after a branch. You see, you remember this is exactly the example that we looked at, and not in this form, but with a slightly different semantic. But the idea is that you cannot bring this before the branch, right? Or at least you cannot do it without doing some additional effort. Why? My question is always, what is the major problem that you have? And the answer is very often exception. It works here, is the exception. Why is it a problem? Because this load should not have been executed potentially, because the branch maybe was taken and so we will not have gotten to the load. Now, if the load I execute anyway and creates an exception, this exception should not have existed, but now it exists, and so it's a problem, right? Because my program will stop because there is an access outside of the bounds that are allowed for me to access, but I never wrote that load. It's the stupid compiler that brought it before the branch. So this is not possible. It's out of question that I do it. The method that Itanium has to do it, because I really need to do this if I want to be efficient, is to bring it before the branch, but do a special type of load. And this load puts in the register R1 in 1 bit more of the register R1. Remember the poison bit that we discussed, they call it here not a thing bit, so is an additional bit. I put in this load puts in that bit the information that there has been an exception potentially, right? And but it doesn't raise the exception. So whereas a normal load, if the load fails, raises an exception, here the exception is not raised, but simply this bit is set. And the idea is that then you can do whatever you want. You can use R1, maybe you make a mistake, so because R1 is wrong and so on, but you keep computing and you compute things that you think are safe until the place where you had the original load. And now you replace the original load, the load you have moved away, but what you replace it with a special instruction that goes and checks this bit of register S1 to see if it is set. And if it is set, it goes and calls some fix-up code. So I think I'll give you a few seconds to think. I hope the mechanism is clear, right? Sort of, I do advance it, but now if the exception should have reported, I'll discover it by going and executing a piece of code. So the question that I want you to think of for a moment is, what is that you are going to write, or actually the compiler is going to write in this fix code? So how do you fix the fact that you had a load? If the load had to be executed, you are confirming that the load had to be executed, but that load had or should have raised an exception, but actually suppressed the exception because of your use of Docker. So what you need to do. Note one thing before I do the stop, that if, on the other hand, the branch would have been taken and I went executing somewhere else, nobody would execute this check of the additional bit in R1, so nobody will check if there was an exception, and the exception will never be reported because nobody checks, nobody looks at it, and so it was suppressed and everything is fine, which is exactly what I want, right? Because this load should not have been executed if I have taken this branch, and so everything is good. So now the question is, again, for you is, what do you expect this fixed code to do? And what is the simplest and most natural code that you're going to put there? Now, this fixed code essentially has to handle the exception, right? So the first thing that you could think is, well, okay, so I can do sort of the exception handler there. One of the problems that you have is that in Itanium, you don't have the cause of exception. You just have this bit that says there has been an exception there. So that is already a problem, but it's a solvable problem, right? You could decide to do Itanium in a different way and save the code. But there is a much more elegant and simple way to do it, which also doesn't force you to try to write exception code in the middle of the user code, right? All this is the code that comes from my program as a user that my compiler is trying to compile. So it's not very elegant also that I have some fixed code that is somehow an exception handler. Actually, it's more than inelegant. It may not be acceptable because I may need it to be in kernel mode for doing these kind of things, right? So there is a much more elegant way to do the fixed code, which is the following, right? What I can do in the fixed code, so in some place else in the code, is to essentially write again load R1 equal R2, the same instruction that is here, but non-speculative. Or if you want, the same instruction that I had in that place. Now I execute it again. And why do I execute it again? Because if there was an exception, because say it was a TLB miss, the exception will happen again. Since I'm now doing it without the speculative tag, I'm just doing a normal load, the execution will be reported, the exception will be reported, and everything that needs to be done for the exception will happen, and we'll execute the load again. And then again in the fixed code, after doing the load again non-speculative, what I need to do is to repeat all the code that I had here that is used there. One needs to be placed again here, copied again here, so that I redo all this calculation based on the new and this time correct value of R1 until I return here to the next instruction, and now I am in a healthy situation. Okay, so I hope you can follow this. If you can't, you can go and look at the documentation that is given for this chapter of our course. There is a paper on Itanium that explains these things. But I think it's very elegant, right? The only problem is that we need to have additional support in the processor to have this special instruction, to have this special bit in all the registers so that we can discover this problem. Now, the same idea, but it's actually not exactly the same idea, but the same philosophy you can imagine for the other problem that of reordering problem that we discussed, which is when I have a store followed by a load. That is also a situation where I would like to bring up my load. Remember, we discussed it not long ago. And we were saying, okay, in many cases, or in some cases, actually not in many cases, what I may be able to do is to disambiguate the R2 and R3 in this example. That is, the two addresses, I may prove that they don't collide. If you can, lucky you, great. But in many cases, in many practical cases, it may be impossible. And it is still extremely important that you try to do this load before, because you need this R1 to do a lot of calculation. And so you would like to bring it before the load. Except that for a completely different reason, you have the same problem that we had before. You cannot do it because maybe it turns out that R2 is equal to R3, and so the value in R1 that you want is not the value that is in this memory location, but is the value that is in R4. And so this is semantically, potentially semantically incorrect. So how do you handle it? And if you look at it from a distance, it looks sort of the same thing, right? I have a load, is not the same, I think it's an advanced load, right? The A as in advanced is an advanced load that I do. I get some value, I use it, I do the store that was sort of the barrier that was preventing me to anticipate. I do whatever I want. When I can, at any point after the store, I do this check R1. And what is this? This is a bit more complicated, but let's come to this in a second. If the check fails, I go into fixed code. What the check fails means is that there has been a collision between R2 and R3. So it's a dynamic situation, right? I noticed that there has been a problem between R2 and R3, or the processor discovered this for me, and since the check fails, I go on some fix-up code. I don't do a pause this time to the fix-up code. You can imagine maybe even more easily in this case. Is essentially the same thing. What I do is that I do again a load from R2. At this point, I'm doing it after the store. So if there was a collision, now I'm getting in R1 the value of R4, so I'm getting the new value from memory, and I redo all the computation based on R1, and basically I have the good value, right? And then I come back from the fixed code that is somewhere else, I come back here, and I continue. If the check doesn't fail, it means that there was no collision, everything is fine. If the check tells me collision, I do this fix-up that I just described by essentially redoing everything that was wrong. Now, the question is, how do I compute this check? How does this check comes? And I let you look at the details in the paper, but essentially, this is more complicated. It's not just that there is an exception and I take the fact that there is an exception and I put it in one bit of R1. Now, to put something in this one bit of R1, which is the same bit that is used for this, but the point is, who puts something in these bits? Well, there has to be something in my processor that every time that I have an advanced load says, okay, what is the address that we are reading? Let me put into a hardware data structure. And every time from this moment that I do a store, I'll check if the address of the store collides with one of the addresses that I am observing, the one I just put somewhere to observe in this data structure. If there is a collision, let me put in R1 one in the bit so that I know that it will fail. There is a failure. So you understand what is happening, right? It's not very different from somehow a load store queue, not quite, but it has the bad component that is also in the load store queue, which is the associative search, right? Whenever I have this store, I have to check R3, the value of R3, with all the values that have been accessed, of the addresses that have been accessed by all the load anticipator, right? All the possible loads, there doesn't need to be only one, right? There can be many. I need to check against all of them if there is a collision. So you see my hardware that was supposed to be fantastically simple, not have any more what is typically the source of slow down or critical path in the control logic, which is this associativity. Well, now associativity came back from the window, right? Because we have associativity again, because without associativity, we cannot do this type of speculation, which is extremely important to us. Okay, so this is one of the examples of things that happen. Here you have the list of all the registers, and you see one thing that is that we expect here, which is this additional bit. You see here also something else that I mentioned before already, both for the floating point and the general registers, the fact that there are 128, which is a very big number compared to practically any other processors, including the hidden renaming registers that often you have in other architectures. Plus, you have some strange feature here, which is these stacked and rotating registers that I will mention in a moment. One of them, the half of this story, the stacked registers, is some mechanism that I'm not going to describe too much. You can follow it more or less from this figure, and actually this figure comes from one of the papers that are cited at the end and are available on Moodle, so it's actually easier that you sort of follow it yourself. What is this? It's a very cute idea that corresponds to avoid having fresh registers at every function call through putting on the stack, because that cost, or passing parameters on the stack and freeing the registers on the stack, because that costs time, right? You have to write on the stack, take from the stack, this is accesses to memory, load stores, and so on, avoids doing this by renaming the registers. That's why they are called stack, right? A register that is called R40, after you do a call, is called, for instance, R32, and you have all the registers here that are free to use already. So R30, 35, and so on doesn't exist until you do a return, and then things get back to the origin. Now, you may remember that I have at least put it on some slides, but I think I have also discussed it at some point very briefly. Spark had the same idea. It was implemented in a slightly less versatile way, but had this notion of register windows. So it will go to a different register window. It will give you a fresh set of registers, or partially fresh set of registers, when you do a call. So again, the purpose was exactly the same. And you probably remember, you possibly remember that I mentioned that it was a very cute idea, but actually turned out into a disaster the moment that Spark had to do out of order, and therefore register renaming on top of what is already a register renaming, right? You see this, right? R40 becomes R32. This is a form of renaming, right? It changes the name of the register in a trivial way, maybe, but it's still a renaming. And combining the renaming needed for out of order execution with this form of renaming became extremely difficult, to the point that Sun Microsystem never made an out of order version, and it's only Fujitsu that took over the architecture that for the first time, much later compared to any of the other competitors, did out of order with this idea. Now, this idea is cute, turned out to be horrible in the situation where people need to do dynamic scheduling, but we are sure that we are not doing dynamic scheduling, so the idea comes back and is actually a good idea, right? So it's good to go and look at literature, because from literature and from history you can learn something that, given the situation, maybe you can do. There is here some details about the Spark architecture, what they do. They have something, again, pretty similar, and how they handle. There is one funny aspect, or maybe useful to teach us something of these architectures, is that what happens if you need more registers, right? Since they give you this architecture, every time that you do a call, sort of gives you fresh registers, right? Here there are all the other registers, so you sort of forget some and have more available. At some point you finish the registers, right? If you keep saying, keep calling, doing one call inside the other, at some point you don't have registers anymore, right? This is a renaming, right? The point is that here there are still the registers that were here. They contain something, but you cannot access them anymore. And here, every time that you move up this stack, you lose some of the physical registers, so at some point you don't have any anymore. So again, maybe you need to read a little bit the documentation to understand a little bit better this mechanism, but I hope you have a sense of what I'm saying, right? So at some point you don't have enough. What happens in Spark is that when you do too many calls too quickly, one after the other, it gives you an exception, and then it's a very strange, not strange, but is a very specific type of exception for Spark, and then of course the operating system of Spark knows how to do in this case, and basically puts on the stack some of the parameters so that you can get again a set of free registers because you now saved on the stack. And one of the things that I find amusing of this Itanium is that to do things um, more easily in some sense for the programmer, for the operating system and so on, it does the spilling, it does the movement of the registers that are still full of some data that cannot be thrown away. It puts them on the stack, but does it autonomously. So it does even speculatively, right? Sort of if I have cycles that are free and the load store units are not being used by the program that you're running, it may decide to spill something on the stack so that if you unlock more registers, you'll get the registers that you asked for. Now, why do I find this amusing, right? Is amusing to me because this is supposed to be a static processor, right? It's a processor that does only and exclusively the things that my compiler says. And now it moves on in reality to do things behind my back that are beyond what even my dynamic speculative processor does, like spilling things directly on the stack autonomously, right? So there is something ironic about this, and more than ironic is actually a way, again, to understand how difficult it is to make these processors work competitively with classic dynamic out-of-order processors. If you really want to compete, you have to start playing these kind of tricks, and these kind of tricks are in practice probably not much easier than doing the out-of-order dynamic schedule. One part also of this, I don't want to go too much in the details because once more you're going to see this in the homework, but it's essentially to do yet another level of improvement on the software pipelining and loop unrolling. Remember that we have seen this loop unrolling as the sort of basic idea, then software pipelining being essentially the same thing but done more elegantly to have as small as possible kernel of execution for a loop. And one of the problems that were left is that we had the prologue and epilogue of our loop, right? Here it was the example that we have looked at ourselves. There was this, that was the new loop rearranged. It was a bit bigger than the original loop, but no big deal. But there was all this stuff before that was the prologue to start the pipelining, to switch on the pipeline, and there was on this side the epilogue, which was the complementary part, all the things that were leftovers to empty the pipeline. I hope you also remember visually when we introduced software pipelining, this schedule that develops, that is your ideal schedule. You cap the center and you say, this is my new loop, but outside of this, there is some initialization and some conclusion stuff that are this instruction here, which take very often many more instructions than the loop itself. Is exactly what you see in this case, right? Per chance. So there is a relatively complicated mechanism that Itanium uses to do this. That is actually extremely sophisticated and very nice, but puts a lot of demands both on the compiler, which maybe is not a big deal, and on the structure of the register file. So the idea is to do exactly the same as software pipelining, but one of the ideas, for instance, is to avoid this part here being the prologue. And how do you avoid the prologue? Is that actually you execute a couple of cycles more the complete body of the loop. So this is my loop. Here is repeated the same loop, and here is repeated. But when I'm doing the prologue and I'm not doing everything, how do I not execute this part? I'm going to use my predicates to achieve this result. And you can look at the technical details on how this works, but essentially the idea is that you have uh, these predicates and actually all the registers that get renamed every cycle, every iteration of the loop. So whatever was called P1 on the first iteration of the loop becomes P2 on the second iteration and becomes P3 on the third iteration. And so if you initialize properly your registers at the beginning with all zeros, your predicates with all zeros, and you predicate, you see here the association of the color, you predicate this part of the loop with predicate number 3, you predicate this part of the loop with predicate number 2, you see here this pattern on the right, and you see on the left that the pink and the orange part are not done on the first cycle, the pink part is not done on the second cycle, and it's only from the third cycle that all predicates being 1, everything is executed. So I let you again look at these technicalities a little bit on your own, because I think it's sort of easier. Maybe these examples help you a little bit following it. But essentially what you need to do is that you need to have all the loop control has to be done not through simple branches, but some counters that decide and inject. You see, for instance, here, inject ones or zeros in the predicate registers in such a way that everything that is rotating rotates in the appropriate way, and you have these sequences of zeros and ones that are available at the right time in the right way. Now, this costs a lot. I think there are some questions that you have even in the homework of how much it costs, because you have these registers, I think it was a few slides before that we saw it, that are stacked and rotating, which means that they are essentially renamed for these two reasons, right? This allocation for at the moment of the calls to have fresh registers, and this rotation every time that you have one iteration of the loop that goes through, whatever was error 32 becomes error 33, and so on and so forth. And these things cost, right? Is a trivial renaming maybe compared to the renaming of our out-of-order processor, but it's still a form of renaming. It's written here, right? This change of all the registers from one iteration to the next, that has some other advantages beside the ones of the predicates that we use here, but yeah, needs hardware and makes relatively difficult to write the code. Here is an example of the code. You're going to hate me because you are asked to do a piece of program of that sort as part of the homework too. It's code that is almost impossible to generate by hand. And that's exactly why you're going to hate me, because I ask you to do it by hand and not by a compiler, but at least it is a very simple case, right? And you see here things that are extremely non-intuitive, in the sense that that the 32 that you get here is one specific register, but if you follow and try to understand all the details, which I let you do offline after the lecture, it turns out that this is activated in one specific cycle, and this is used 2 cycles or 2 iterations later. So this 34 is actually 32, register 32 of 2 iterations before. So whatever you put here, when you do twice this loop, you'll find in register 34. So it's extremely counterintuitive, right? Because, I mean, you say R34. You look here, nobody has ever written in R34, so this code looks wrong, right? And actually, no, but it depends. There is a correlation between the P's and the predicates and the registers that you use and how many rotations there have been in between. Why all that? If you look at the code, this is actual real Itanium code for, look, what is the code is the usual thing, is the adding a constant to a vector. So it's always our example for the nth time, but look at what it is. There is no prologue, no epilogue, and the body is extremely compact to the point that the loop is a single very long instruction. So it's sort of the ultimate solution for this problem of unrolling software pipelining and so on, and it is called modulo scheduling. Fairly difficult to put in practice, but actually extremely elegant and effective. So I'm basically finished about this Itanium chip, and maybe we need to move on to some of the conclusions. One of the things that you could observe when Itanium 2 existed, and we are talking around almost 20 years ago, in the even second commercial implementation that came out, is that, for instance, at the time, it was the only processor ever that had an L3 on-chip cache. So now it's maybe more normal that there is, but at the time there was no other product had it. The die, not unrelated to this having the L3 cache on chip, was huge. And when I say huge, I don't mean simply it was big because sometimes maybe I've said Intel needs to sell you a relatively important piece of silicon to make the price being interesting. This is a huge piece of. This was much bigger. It was probably one of the bigger commercial processors at the time. So why that? Well, you can imagine, right? If this kind of processor has a huge problem if there is a cache miss, because if I have a cache miss, I have to stop completely execution. I don't have to stop only the load that has a miss, but everything else can go on at least until my dependencies allow me to execute something. I have to stop everything, right? Because every instruction, the load is in parallel with the number of instructions that should go with it, and everything that follows should also follow exactly at the right time and monolithically. So I have to stop everything, and that is very bad. And that probably explains why it is important to have an L3 on-chip cache, so that I have very few misses, or the minimal number of misses that I can afford to DRAM. So here is again an example. Here is an internal view of the pipeline, and of course you cannot tell very many things from this, because okay, it's very sort of artistic representation, but you still see some of the things that you imagine, right? You have here the instruction buffer with these bundles. Now you do the dispersal, that is, you send it to the right places. Remember maybe my crossbar in one of my first slides, where you decided, depending on the functional units that you are targeting, to send it. And then you have, well, you have the renamer of the registers, because you have this stack and some problems of renamings that you should not have, right, in very long instruction words, but because of these stacked and rotating register, well, there is something. It's probably way more trivial than in the x86, for instance. And then you have the different units that are in parallel and so on and so forth. One of the things that you notice here is, for instance, this scoreboard and hazard detection. And here, if you are puzzled, you have every reason to be. You have been told that this is a very long instruction word processor, that is a processor that doesn't do absolutely any check of dependency at runtime. And surprise, surprise, and now there is in the processor something that is hazard detection. I have no idea what it is, but it doesn't look good. And scoreboard, and scoreboarding is something similar to reservation stations and these kind of things. Again, something that is totally unrelated. Now, I don't know exactly what this means. I cannot tell more precisely, but you see that there is this box disconnected from everything but in here. Okay, does it work? So here is a table that we have seen already. You see some of the numbers. The numbers are not necessarily bad, right? You see here for 2 cores, the spec int and floating point, and you see here corresponding numbers for Xeon cores of the same time, and the results are reasonably good. So you can be competitive. It's interesting to figure out also at which price. Here you have 170 million transistors to realize this processor that has this kind of performance. Here you need 1.72 billion transistors. Now you see the difference, right? The difference is not little, it's not a small difference. It's what is it? Now I lost the thing. Is almost exactly 1 order of magnitude, right? So it's a huge difference between the two. For a difference in performance that then looks relatively small at this point, right? Because it's only 30% or something of the sort. It's interesting to see maybe the clock rate. This processor is going at almost 4 gigahertz, and this processor, let me remember, what did we do this for, right? We said, oh, it's great to remove all these control paths and so on, so that we have a processor that can go at a much higher frequency, or at least the critical path moves away from control. Aha, interesting. Actually, our frequency has gone down by a factor of 2. So there are a few considerations of this sort that you can have. It's true that you can do an issue rate that is higher if you find instructions that you can find, whereas in the Intel Xeon, you are limited to 3 instructions, and it is almost the same for every other even manufacturer. But you get a sense of how difficult this is, right? It's really a fairly difficult business. So the result is that it's gone away. So the VLIW Alaitanium has disappeared. What is the morality of all this? So first of all, I think it's important to discuss VLIWs for at least one reason. And the reason is that I believe going in the direction of static scheduling is an absolutely natural idea. Remember, we had it on maybe the first lecture when we said, okay, what are the things that I can do? I can put hardware in my pipeline to stall it, or I could modify my code. And I think we concluded that actually modifying the code was not a particularly bad idea. Now, it is not a bad idea, and I want to stress, I'm not saying that VLIWs are a bad idea and one should not do this. I think the point is very well captured by this sentence from the NSE and Patterson. And it says that it is a mistake to think that there is a simple approach to multiple issue processors that does not demand a significant investment in silicon area or design complexity. What it says is you have to sweat somewhere. It may be in the hardware, it may be in the logic for doing the issue out of order. If you don't do it here, you'll do it somewhere else. You'll do it in the compiler, and the design complexity will be in making a compiler that it works. What will not happen is that, oh, look, why do I do this in hardware? Let me ask my compiler friend and get him to do this job, right? That is what doesn't work. So it's important to understand what are the limitations of VLIWs so that one can go in that direction only when you understand what is the what are the limitations that come with it. And maybe you understand that there is no problem. So let's go back to the question. So what I just said about Itanium means that there is no VLIW around in the world and nobody wants VLIWs? Absolutely not. The contrary is true. You have probably several VLIW processors in your laptop, not in the primary processor, but in all the communication devices that you have there. You have several, at least a couple, that are inside your cell phone. And what do? They are applied in very specific situations where they do signal processing, which are a bunch of algorithms that have exactly those characteristics for which many of the problems that we discussed in the last few hours do not apply. They have accesses that are very easy to disambiguate. It doesn't matter if the user has to give a lot of help to figure out what is the best transformation, because the code is written once and for all by the manufacturer, so someone can spend 1 man month to try to do the optimization. And a few things like this. So the code base is relatively small, so you can make sure that it fits the cache and so on and so forth. So you see here, for instance, one of the most famous, or the blueprint of several of the most famous DSPs. TI, Texas Instruments, is one of the market leaders of DSP processors. There are others from other manufacturers, but they are all very similar to this. And how do they look? They look exactly how we think a VLIW must look, and in fact, much more than what we have seen in the Itanium. We have a register bank here. We have all the values that come out from the register and go into all the units and the results that go back in the register bank. And basically what my code says is what this ALU has to do on this cycle and in the second ALU and so on. And it's a little bit more complicated, but sort of not fundamentally, in the sense that there are two different parts, two different register banks and set of units that operate in parallel. So it's what is called a clustered architecture, in the sense that there is one cluster that seems to be really very much as a pure VLIW, and a second cluster that seems to be an independent, but actually time-locked, synchronous second VLIW that operates at the same time. So to come back again, static scheduling is not a bad idea, but is an idea that works only in specific situations. If you are in those situations, it's fantastic. Why people use this is because they are very cheap, and I can put many in my $20 Wi-Fi card. I can put one of these to do the signal processing that I need. In other situations that are not this one, they are a disaster, and is essentially what we have seen with the Itanium. This almost completes what we are going to do about static scheduling. We'll just come back to one little part. this idea of dynamic binary translation, which has been, at least has been developed to handle the incompatibility between different versions of VLIWs, the problem that we have put aside and decided to ignore, is actually a technique that is much more general than that, but we'll maybe tell it in this framework of VLIWs because that's how it has been mostly developed.